So, the design intent of these activities is that you collaboratively work on question 1. Once you come to a consensus answer on question 1, you then move on to question 2 and collaboratively work on question 2, and so on as you go through. Okay, so upcoming due dates, we talked about tomorrow. Wednesday at 5, the small group activity number 2 quiz will be due, and the content video quizzes will be due. There are quite a few of them this time, but notice that a bunch of them are really short, about 2 minutes long. And I am interested in feedback on whether or not having these shorter ones is preferable to having some longer ones, because all of these osmotic pressure, or excuse me, all of these colligative properties ones could have been combined into a 4, 6, 8, 10, one 10-minute video rather than 4 videos between 2 and 4 minutes. I don't know that I have a strong preference myself on which way it's done. I've been told by people who've done studies on this that you want to try to keep content videos to about 5 minutes, just for an attention span kind of thing. But I'd be curious about any feedback you guys might have about that. And then Friday, of course, we have the homework. There are 4 parts to it this week, and there is not a supplementary question this week as well, because I am still trying to catch up on the previous ones. Okay. Any logistical questions before we move on to some muddiest points and some content? Could I show you one? The little numbers. Oh, yeah. No, it's fine. So let me, oops, go here. We are trying to get our learning assistant in to the class session. Got it? Okay, all right, good. All right, any other logistical questions before we get going on content? Okay, so we have a bunch of muddiest points this time. We've got 2 sheets of them. We're gonna start here with some stuff that's on activity 2, group activity 2, since that is the item that has the nearest deadline. So, some confusion about what the C and the X dilution measures are meaning. One person asked, does 1C mean 100 milliliters and does 1X mean 10 milliliters? No. 1C means dilute by a factor of 100, and 1X means dilute by a factor of 10. So if you start with 1 milliliter, then 1C means you dilute it to 100 milliliters. But if you started with 5 milliliters, you would dilute it to a final volume of 500 milliliters. Okay? So it's the factor by which you are diluting. Okay? Next question here is, if you're doing a 4x, does that mean that your overall dilution is 4 times 10, or a factor of 40, or does it mean 10 to the 4th? Well, let's think about that for a minute. So if we are doing a 4x, what we do is we take 1 milliliter and we dilute it to 10. Okay? We then, after mixing this all up, we then take 1 milliliter from that and dilute it by another factor of 10, up to 10 milliliters. And so then you repeat this process 4 times. So you've diluted by a factor of 10, by a factor of 100, by a factor of 1,000, by a factor of 10,000 as you go across here. So you are getting to 10 to the 4th as how much this has been diluted relative to what you started. This is the concept of sequential dilutions. Checked off the wrong one. Okay. One of the questions asks about the inverse of concentration to get the volume necessary to have 1 molecule of solute. So let's talk through this idea using an example. So let us suppose that we have a sample that is 0.0001 molar in whatever our solute is. Okay. So what does molar mean? Anyone here or in the chat? A little louder? Moles per liter. Yes. So this, it means moles of solute over liters of solution. Okay? Now, let's take the inverse of this. Okay, so 1 over this. So 1 over 0.0001 moles of solute per liter of solution. Okay? So that tells us, if we do this, we get 10 to the 4th, or 10,000 liters solution per mole of solute. So think about those units for a minute. That tells you the volume that is necessary to, of the solution to have a mole of the solute. Now, we know that that we can convert from moles to molecules by using Avogadro's number. So 10,000 liters solution over moles of solute. What is Avogadro's number? 6.022 times 10 to the 23rd molecules, or atoms or ions, whatever it is you're dealing with, per mole. We want moles to cancel, so we need moles in the numerator here, right? This is dimensional analysis. So we want moles over molecules, which means that we put the 6.022 times 10 to the 23rd in the denominator here. Now, if we do this calculation, we're going to get some number. So basically, we are going to, well, let's see. Let me see if I can do this, if my phone calculator is up to the task. So 10,000 divided by 6.022 times 10 to the 23rd. And I get 1.66 times 10 to the minus 20th liters per molecule, which means that you need this amount of liters of the solution in order to have 1 molecule in it. okay, on average. So that's the general idea of what this question's asking about, is if you have a really low concentration, so this may seem like a really low concentration, you ain't seen nothing yet. This is absolutely enormous compared to homeopathic remedies. And so when you get to a really low concentration, this volume, in order to have a single molecule of the compound in it, of the active ingredient in it, is going to start to become large. And so that's what we're trying to look at in this problem. And you can figure that out just from dimensional analysis. Any clarifying questions on this concept? Okay. So there's a question about how much water would you need to use to create the same solution using the C method if you start with 1 mL of the sample at each step, or use how much water would you need to create the same concentration of a solution in a single step if you start with 1 mL of a sample. And so trying to understand what that's actually asking for. So there's a series of questions where you are creating a 10x solution. You are then trying to determine the what this same dilution factor would be in C, and then we're going to do it as a single step. Okay, so let's talk about the 10x dilution first. So you start with 1 mL. You dilute it to 10 mL. Okay, so you have added 9 mL of water in that step. So that is 1x. 2x means we then take 1 mL of this, dilute that to another 10 mL, meaning we have added another 9 mL of water. So we're adding 9 mL at each step. Right? The final concentration, and at each step, the concentration goes down by a factor of 10. So that means that our concentration is going to be 10 to the minus 10th of what it was when it started. Because it went down by a factor of 10 the first time, another factor of 10 the second time, and so on, all through 10 of them. And each step you're adding 9 milliliters, so it's going to be 9 times 10 to give 90 milliliters of water that you're going to have to use to get there. Does the general procedure here make sense? Okay, I'm seeing some nods, good. Now we want to get to the same level of dilution in the C method, where we still want the concentration to be 10 to the minus 10th. But we're now going down by factors of 100 instead of factors of 10. So how many times do we need to do that in order to get to a dilution of 10 to the minus 10? 5, right. So instead of going 10, 10, 10, 10, you do 100, 100. If we were going down to 4x. By 10x, we're going down to 5c. So same idea. 1 mL getting diluted to 100 mL, meaning that we added 99 mL of water with each step. So the amount of water that we had to use was 5 times 99. which is 495 mils of water. So you have fewer steps here, but it took quite a bit more water to do it. Does that make some sense? So then the next question is asking about doing the same thing but in a single step. So that means you're still wanting the concentration to be reduced by a factor of 10 to the minus 10, but we're doing it with a single dilution step. How does that work? If you want to reduce the volume by a factor of 10 to the minus 10, and we start with 1 milliliter, what does our total volume need to be? In milliliters. Well, in a single step here, we're diluting by a factor of 10, and we're going up to 10 milliliters. In a single step here, we were diluting by a factor of 100, and we used 100 milliliters. In a single step here, we're wanting to dilute by a factor of 10 to the 10. How many milliliters do we need? Ten to the 10. Let's write that out. So how many did we add? Well, we started with 1 milliliter of this, of the sample. We diluted to this amount. So it's that much. Okay. So, and the next question is asking you basically how many swimming pools worth of water is this? Okay. So that's the thought process we're going through here. We are trying to evaluate what these homeopathic remedies are like at like 10C. But remember, 10C is not even close to a typical remedy that you're going to find being sold. Typical remedy is 30C. Okay, so that's where this is going. All right, any other questions on the concepts in the activity that we're dealing with? Either chat or live. Yes. Say it again. The second question, is 4x meaning 4 times 10 or, okay, sure. So looking at this, so this idea is that what 4x means, okay, if 4x meant you dilute by a factor of 4 times 10 or 40, what that would mean is that we're taking a milliliter and adding 9 milliliters to bring it up to 10, then to that entire thing add 10 more milliliters to bring it up to 20, then add 10 more milliliters to bring it up to 30, and then 10 more milliliters to bring it up to 40. That's what that would mean. But that's not what 4x is telling us to do. 4x is telling us to take 1 milliliter and dilute it to 10. Mix it all up. Oh, sorry. Thank you. Is to take 1 milliliter and dilute it to 10. So that whatever your concentration was before, it's now 10 times less concentrated. So if you started with 1 molar, it's now 0.1 molar. Okay? Then take 1 milliliter of that. You take 1 milliliter of that and then dilute that by a factor of 10. So then if this step started at 0.1 molar, diluted by a factor of 10, it gets to 0.01 molar. Okay? 0.001 molar, 0.0001 molar. Okay? So that is diluting by a factor of 10,000. Is that making sense now? Okay. All right, anything else on the aspects of solutions and dilution having to do with the activity? Yes? Give an example of what?
Like number 16, I'm just confused on what they're asking, I guess.
Okay, so remembering that 1 milliliter equals 1 cubic centimeter, how many moles of arsenic trioxide are in that initial 1 milliliter? So scroll up slightly. This is asking about question 16. Notice that you are given a density right here. So you have a density which is 3.74 grams per cubic centimeter for the arsenic trioxide. So if you're taking 1 milliliter, that's 1 cubic centimeter, given the density, you can now know how many grams you have, so 3.74 grams. Now you convert that to moles. And given that you are, and you should be given arsenic trioxide's empirical formula somewhere. Scroll up. No, down. So you may need to look up the empirical formula for arsenic trioxide. It is either arsenic 03 or it's arsenic 203. I think it's the second one, but you'll need to look that up. And that is going to, you use that with the density in order to determine the number of moles you have in that 1 cubic centimeter or 1 milliliter. Okay. All right, anything else? Okay, it looks like the chat is confirming that it's AS203. Thank you. All right, so let us then, we'll consider these done for now. Let's look at a variety of other topics we have. So solutions in general. Looking at the questions, when do solids and gases form solutions? And the examples we're coming up with alloys, smoke, air, the aroma from acetone, things like this. So alloys are an interesting example. They are typically a solid in solid solution. And the idea is, and these typically form with metals. So the idea in a metal is that you have a crystalline lattice of the metal cores, so the nuclei and their core electrons, floating in an electron sea of the valence electrons. Okay. What that means is that if you take out one of those metal cores along with its valence electrons and replace it with the metal core and the valence electrons for some other metal, that probably shouldn't cause a problem. So you should be able to mix in different metals to form sort of a blend. Now, why isn't this just a compound? Why don't we, if for example, we take, I'm trying to remember an example. I think sterling silver is silver and tin, if I remember correctly. Ag and tin. Why don't we call that a compound? Why are we calling this a solution as an alloy rather than a compound? Any ideas? Yes? Something about charges? Okay, so you would need to have Ag plus or Ag2 plus or something like that? Okay, well, if it were paired with a nonmetal to make a salt, that's probably true. But here we have two things that are both metals that are being added together, and neither one of which is particularly electronegative. So in that case, nobody's really grabbing the electrons very tightly, and so that's why we use this electron sea model of the cores kind of floating around in this sea of electrons. Any other ideas? Yes?
From the chat, Logan said it can have different concentrations.
Different concentrations, that's exactly correct. If this were a compound, then there would be a definite ratio between these two, maybe Ag2SN3 or something like that. But that's not what we see experimentally. What we see experimentally is that we can have any ratio we want between silver and tin, and it will form a continuously varying range of concentrations and continuously varying range of properties as it goes through. So that sounds a lot more like a solution than it does a compound. Okay, so that's what's going on with alloys. Smoke. So what is smoke? Anybody have an idea? We could sort of call the air that the smoke is floating in a solvent, right? What's the bits of smoke? Yes. A colloid, right. And so I didn't actually assign that chapter of the textbook. I'm appreciative that somebody went ahead and read that chapter. But what it is little particles of stuff, typically amorphous carbon or something similar to that. And those little particles are floating around in the air. So smoke is a two-phase system because it has solid pieces dispersed in a gaseous medium. So a solution, by definition, is homogeneous, meaning that there is one phase. So if a gas like oxygen dissolves in water, like seawater, which ends up allowing fish to breathe, that oxygen in water solution is a solution because it is homogeneous, because there are not pockets of air and pockets of water. It's uniform throughout. Smoke, on the other hand, is a gaseous medium with distinguishable particles that are larger than molecular size floating around in it. As sort of an interesting aside, molecules are probably on the order of about a nanometer in size, small molecules anyway. And light will scatter off of particles that are close to half the wavelength of light. And light is typically anywhere from about 300 or 400 nanometers up to about 800 nanometers, okay? So if you've ever seen a laser show where they have smoke and then they shine a laser through it, you see the path of the laser going through the smoke, because the particles in there are large compared to the wavelength of light. The particles are on the order of hundreds of nanometers, and so the light can bounce off of it, and we see that light bouncing off of the smoke towards our eyes. If you shine a laser through the air with no smoke present, you won't see it except where it ends up hitting, because there's nothing it's bouncing off of. Okay, how about air itself? Air itself has multiple components to it: oxygen, nitrogen, carbon dioxide, and so on. Is that a solution? I see a nod. Yes, it is a solution. It is homogeneous. You could change how much nitrogen there is in the air by taking a tank of nitrogen and opening it up and letting it out. And you can continuously vary it. So air is not a compound, it is a solution. And it is homogeneous, so it is a solution. Okay, the aroma from acetone. That's an excellent one, example to use. So acetone, when it vaporizes, have you guys in Chem Lab used acetone yet for anything? Sometimes that's used to like rinse glassware so that it'll dry quickly. Maybe you haven't. Okay. Acetone is one of the primary components in most nail polish removers. So that smell from nail polish remover is what is acetone typically. What you're experiencing there is the vapor pressure of acetone. So remember that all substances have a vapor pressure because some small fraction of the molecules have enough kinetic energy to escape their intermolecular forces into the vapor phase. And so then asking, is this a solution? You need to think about whether or not what you're experiencing when you smell the aroma are little droplets of acetone that are floating around in the air, similar to smoke, where it's little particles of solid, or is it individual molecules that have vaporized? What do you guys think? From our sort of kinetic molecular theory explanation for how vapor pressure works. You want to say individual molecules, and you'd be right. Yeah. So if the acetone molecules, gain enough kinetic energy to escape the liquid phase, they do it individually. That's right. So this is indeed a solution. Okay. There was a question about liquid-liquid solutions and trying to understand miscible, immiscible, and partially miscible. To look at that one, I am going to call up a video that I did. Where am I going? I'm going here. Let me go to sharing screen so that the folks at home can see. Content videos. All right, which one was this? Solubility. Okay. Okay, and oh, actually, hang on. I'm going to go to the YouTube version rather than that, so that we don't have to deal with the quiz. Okay, so I'm just going to fast forward here to some images. So I like, stop. There we go. Okay, so the idea of miscible liquids is that they will mix together into a solution at any relative concentration. So if we look at this diagram here that I'm circling with my cursor, we have liquid A on top going from 100% down to 0%. We have liquid B on the bottom going from 0% to 100%. And I've colored liquid A to be red, liquid B to be blue. Okay? And what we see is that for miscible liquids, we see a gradual transition from red to blue as we go across, because we can mix these into at any ratio we want, and it forms a single phase. Okay? Immiscible liquids are liquids that do not combine. So same thing here, liquid A goes from 100% to 0%, liquid B goes from 0% to 100%. We have two phases, the red phase and the blue phase, and they never mix. So at any particular ratio, we're going to have a red layer and a blue layer, and by changing how much of each one you have, you're simply changing how big the two layers are. Okay? So those are immiscible liquids. So the canonical example for immiscible liquids are oil and water. Now, these are great as sort of ideals, as extreme versions of what's going on, but a lot of things actually happen partway between, partially miscible. And so the idea is that in liquid A, you can dissolve a little bit of liquid B. Okay, so going up to about probably 20% in this example here, you can 80% A, 20% B, it'll form a solution. But liquid A can't hold more than that. And so beyond that, you start to get a phase separation. Similarly over here, you can have liquid B and then dissolve a little bit of liquid A into it. But again, you reach a limit. And that limit, in this case, probably around 18%. And in this case, that limit is an amount of A beyond which you can't put more into the B phase. And so in between those two limits, you have two phases. One of them is mostly A with a little bit of B dissolved in it, and the other one is mostly B with a little bit of A dissolved in it. Okay? And where you are in this range tells you how much of each of those two phases you have. So that's what's meant by partially miscible. You can, in fact, mix them into a solution, but only over some limited concentration ranges. Okay. Now, these cutoffs that you have are going to vary with temperature. And so what I have here, if we imagine this being at a single temperature and all we're doing is plotting what percentage is this at, what percentage is this line at, go a little bit further, we get something that looks like this. Okay? So you have a one-phase region here, a one-phase region over here, and a two-phase region in the middle. But you change the temperature, and you can change where those ranges are, and you might even be able to reach a temperature where it becomes completely miscible. Now, this is going into much more detail into partially miscible than the textbook does. But it gives you a much more concrete, a much more realistic view of how material solubility works. Yes? Oh, okay, I'm sorry. Any questions on these ideas of miscibility, immiscibility, partial miscibility? Let me stop sharing there so I can see the chat if there's anything. Okay. So, there was a question about the difference between dissolving and disassociating. So dissolving means it goes into solution. Disassociating means it breaks into its constituent parts, usually ions. So it is possible for, generally when we use the word dissociate, we are talking about an ionic compound, or we're talking about something like water, which can separate in water into H plus and OH minus. Okay. But there are certainly things that can dissolve without dissociating. So if we take sugar, for example, which is non-ionic, and dissolve that into water, it dissolves, but it does not dissociate because the sugar molecules do not break apart. Okay. I'm going to come back to these because I don't know how we're going to end up doing on time on stuff. I'm going to try to address more things having to do with concentration and such because that's going to that's going to be more important for the group activity. And if we have time, we'll go back and do some of the energy and entropy stuff. We'll come back and do some of the energy and entropy stuff. And if we don't have time to do that, then we'll do that in tomorrow's class. All right, concentration measures. What is the difference between molality and molarity? Okay, so capital M refers to molarity. Lowercase m refers to molality. This is moles of solute over liters of solution. This is moles of solute over kilograms of solvent. Okay. So there is one situation in which numerically you get the same values here. That situation is when you are looking at dilute aqueous solutions. Because if it's dilute, then if you're measuring the amount of solvent, that's almost identical to the amount of solution, right? And if it's aqueous, then we have 1 gram equals 1 milliliter, right? And so if 1 gram equals 1 milliliter, then what does a kilogram equal? 1,000 milliliters is from the chat, a liter. Right. So in dilute aqueous solution, a liter of solution is the same as a kilogram of solvent. Now, in most of chemistry, we use molarity. And so, on the activity, I recommend that you use molarity because that very directly gets you from the amount of solution to the number of particles of solute that you have. The reason molality is introduced primarily is for colligative properties, which we're going to get to in a little bit, because a couple of the colligative properties that we are looking at, freezing point depression and boiling point elevation, are traditionally determined in terms of molality instead of molarity. So that's the primary reason that we even talk about it. Okay, any questions about that distinction? Okay, all right. In general, how do you know if you're using solution or solute in the denominator? Well, the only real case that I remember where we use, okay, first of all, we never use solute in the denominator. We would use solvent in the denominator occasionally. And I believe that the only example of using solvent in the denominator is molality. I may have misremembered one, but it certainly is the primary one. In most cases, we are dealing with a fraction of the whole, so like mole fraction or ppm or anything like that, mass fraction, volume fraction, any of those. Because it's a fraction, it's a part of the whole, and so you want the whole, meaning the solution in the denominator. And molarity is the same kind of thing, but just in mixed units. Okay. Reversing ppm or ppb, can you work backwards to find the mass of either the solution or the solvent? And absolutely you can do that. So if you have a 10 ppm solution, and you know, which means that you have 10, let's say we're doing mass by mass, 10 grams of solute over 1 gram of solution, and this has been, to get ppm, we have already multiplied this by 10 to the minus 6. So this is going to be 10 times 10 to the minus 6 grams of solute over this. Then yes, if you say, I want this much solute, you just run the calculation backwards to find out how much solution you need. Okay. There's been some confusion about ppm and ppb with respect to mass, units of mass and units of volume. So let's look at, one of the issues we have is that ppm, ppb, and ppt for trillion, these are simply saying what magnitude of ratio are we looking at. It doesn't tell us whether it's a mass to mass ratio, whether it's a volume to volume ratio, or a mass to volume ratio. And so we generally have to determine that from context, or sometimes they will say ppmw, where W is meaning weight, which we understand as mass, or ppmv, where they mean volume. But very often they don't, and so you have to have some other kind of information to determine which one they're talking about. But since it's a fraction, what you do is you take the, say, mass fraction, so mass of solute over mass of solution times 10 to the 6th to get the ppm. If you do this, as long as this is in the same units as this, it doesn't matter. You have the same ratio. Okay? So this could be grams, it could be ounces, it could be anything you want. It could be AMU, atomic mass units. It could be anything you like. The only confusion comes in when we're dealing with what's known as mass per volume units, which is this sort of bastardized version of a unit that really doesn't make sense, and it's unfortunate that it has caught on in biology and pharmacology, because what they are doing here is they are assuming that we're talking about a dilute aqueous solution. Because remember that 1 milliliter of water equals 1 gram of water. So what they are doing is saying that mass and volume can be interchanged as long as you're dealing with milliliters and grams. And so if it's a mass per volume unit, you need to use milliliters and grams. But it's not really a true fraction. And the problem is that this M per V type of unit, even in pharmacology and in biology, is used in plenty of cases that are not dilute. And when it's not dilute, if you've got something really heavy or really light dissolved in the solvent, the density is going to change sometimes quite a bit. And so this is a horrible unit that unfortunately, depending on what field you go into, you may be running into. Okay. All right. Understanding C1V1 equals C2V2. So this is a very useful, very powerful equation that, if you stop and think about it, is really easy to understand. Let's assume that we are talking about concentrations in terms of molarity. If we are doing that, then what do you get if you take a concentration and multiply by a volume? Just think about it from a dimensional analysis standpoint. Molarity times volume equals what? Moles. Moles of what? No. So the choices are moles of solute, moles of solution, or moles of solvent. Solute. So if you take a concentration, say 1 molar, that means 1 mole solute per liter solvent, and you multiply this by a volume in liters of solvent, that cancels and you get moles of solute. So if you have 15 milliliters of a 0.38 molar solution, and we multiply those things together, we get the number of moles of solute that we have in here. Okay. So let me just do that real quick. 15 times 0.38 is 5.7. So we find that we have 5.7, so if it's in liters, to make it cancel, 0.015 liters, okay? So we get 0.0057 moles of our solute. Now, if we dilute this, if we take, I'm sorry, it's not, I didn't put that on screen. So if we take 15 milliliters of our sample, that's 0.38 molar, we know how many moles we have just by multiplying the two together. Now, if we dilute this to something else, have we changed the amount of solute we have? No, we have not, because all we've done is add solvent. So that means that whatever our number of moles of solute are here, that same amount of solute has to be here. So what's our new volume? Okay, well, we have this on the left. Our new volume, let's say we go up to 50 milliliters. Well, so that means this equals whatever our new concentration is times 50, or 0.050 liters, right? So then you just solve for C2, and notice if you divide by 0.050 liters here, you get moles per liter. So it becomes molar, which is the units you wanted for a concentration. So all this equation is doing is saying when you dilute something, you don't change how much solute you have. That's it. That's the entirety of that equation. Now, the question then becomes, can you use any concentration units as long as they are the same? And I'm going to extend that and say, can you use any volume units as long as they are the same? The answer is yes in both cases. Why? Because if we have C1V1 equals C2V2, and our concentrations in molarity, but our volumes in milliliters, right? Then that means on this side we need a conversion factor that goes from milliliters to liters. But then we need that same conversion factor on the right-hand side to go from milliliters to liters. And so those conversion factors are just going to cancel out. So as long as the volumes can be any units, any volume units you want, as long as they're the same. Okay. How about concentration? Well, yeah, it's going to be a standard conversion from molality to molarity, and you're going to have the same thing on both sides. Or ppm to ppm to molarity, same conversion on both sides. So they just cancel out. So yes, as long as you are consistent in your unit usage on both sides of the equation, your concentration units and your volume units can be anything you want. Okay. All right. Looks like we got that part done. How are we doing on time? Okay, I've got about 4 or 5 minutes left. So where'd my other list of questions go? I had another page. Here it is. Okay, so I'm obviously not going to be able to get to everything. We have a set here on energy and entropy in solution formation. We have some questions beginning to talk about colligative properties, and then a revisiting of some week 1 material with intermolecular forces that are on the list here. Given that we only have about 4 minutes left, I will take requests from either the class here or in chat. If there's one of these that you'd rather I focus on in these last couple of minutes, or if there is something else you'd like me to look at. Anything I don't get to today, I will do tomorrow. Okay, I have a request from the chat for the colligative properties part. Okay, so colligative properties are simply are properties that depend on the amount of solute only. So, and they do not depend on the nature of the solute at all. So if you have the same concentrations of different solutes in the same solvent, then the effect on the colligative properties will be the same. So we have 4 colligative properties. We have vapor pressure lowering. We have boiling point elevation. And these two are directly connected to each other. If you think about why boiling point, what boiling point means, you'll see how those are directly related. There is freezing point depression. And then there's the oddball out osmotic pressure. All 4 of those depend only on the number of solute particles you have, not on the nature of the solute. And so if you have the same concentration of different things in the same solvent, their effect on the vapor pressure, their effect on the boiling point, and so on will be the same. So that's the essence of that particular question. Okay. I also have a request on energy and entropy from the chat. Okay, we have several questions associated with energy and entropy here. So I'm going to have to just pick a couple to look at. So one of the issues is that kind of permeates a couple of these things is that Newton seems to expect you to be able to take numbers for entropy and enthalpy and turn that into whether or not a reaction is spontaneous or not, whether or not the dissolution is spontaneous or not. And the problem, I wish I had the ability to cancel out individual questions from Newton, but I don't seem to have that ability. We have not covered that yet. So that's why you don't know what's going on with that. If you're trying to answer those questions, what I will do is tell you that, we've talked about delta H for enthalpy and delta S for entropy. There's a related quantity delta G that equals delta H minus T delta S. Okay? So if you're given a delta H and if you're given a delta S and you know the temperature, you can calculate this delta G thing. And if delta G is less than 0, the reaction is spontaneous. If delta G is greater than 0, it is not spontaneous. Okay, so let's think about this. If this didn't matter, delta H positive means exothermic, and that would correspond to something spontaneous. If delta H doesn't matter, then we have a negative T delta S, and remember T we're measuring in Kelvin, so it's always a positive number. So if we have a positive delta S, then its contribution to delta G is going to be negative, and negative means spontaneous. Okay, so an increase in entropy causes something to be spontaneous. An exothermic reaction causes it to be spontaneous. When the two point in different directions, well, it depends on what temperature you're at as to whether the overall thing is going to be spontaneous or not. So if you're trying to solve a problem in Newton about this, this should give you enough information to do it. I am not going to ask any exam questions on this until we actually cover this in this class, which is going to be later in the semester. Okay, so I hope that helped some, and I am out of time. Thank you all. Good questions today.